Imagine you have a clear liquid in a small glass cell. Dissolved inside is a chemical compound, but it is completely invisible to the naked eye. How do you figure out exactly how much of it is in there? The answer is to use a spectrophotometer. This machine shines a specific wavelength of light directly through the sample. Even if the liquid looks perfectly clear to us, the dissolved particles will absorb some of that incoming light, causing the beam to dim before it exits the other side. We can calculate exactly how much dimming occurs using a simple mathematical formula known as the Beer-Lambert Law. A equals epsilon times B times C. In this equation, A is the total absorbance, literally how much light was blocked. The B stands for path length, which is just the physical width of the cuvette, and C is the concentration of our invisible particles. These are the physical macroscopic variables that we can easily measure or control right at the lab bench. But while this math tells us exactly how much chemical is present, it relies entirely on that first variable, epsilon, or the molar absorptivity. To understand what that constant actually is, we have to look past the liquid itself and examine the quantum nature of the molecules. When we zoom down to the atomic level, we find that an entire molecule does not absorb light uniformly. The absorption is handled by specific covalently bonded groups of atoms, like a carbon-carbon double bond. We call these localized light-absorbing regions chromophores. When a photon of UV or visible light hits a chromophore, it triggers a quantum event. An electron absorbs the photon's energy and jumps from its stable, resting orbital into a higher energy excited state, known as an antibonding orbital. These electron jumps require very specific amounts of energy depending on the bonds involved. For instance, breaking an electron out of a tough single sigma bond, a sigma to sigma star transition, requires a massive vertical leap in energy. Because these take so much energy, they only happen in the extreme vacuum UV region, making them hard to measure in a standard lab. However, electrons in double bonds, or the non-bonding pairs on oxygen and nitrogen atoms, are held much more loosely. These pi to pi star and n to pi star transitions require much smaller leaps of energy, putting them within the range of standard UV-Vis spectrophotometers. Because the specific structural arrangement of a chromophore dictates the exact size of these energy gaps, it creates a unique molecular fingerprint every time it interacts with light. But molecules are complex. A chromophore rarely exists in total isolation. It is constantly influenced by the neighboring atoms attached to it. This brings us to the auxochrome. Think of an OH or NH2 group. On its own, an auxochrome doesn't significantly absorb UV light, but it acts as a chemical modifier when attached directly to a chromophore. It works by sharing its own non-bonding electrons with the chromophore, physically extending the overall conjugation, or connected electron system of the molecule. By extending that conjugation, auxochromes alter the amount of energy required to excite the chromophore's electrons. They effectively rewrite the molecule's fingerprint without being the primary light absorber themselves. So how do we actually see these structural modifications? We look at the data output from the spectrophotometer, plotted on a graph called an absorption spectrum. This graph illustrates exactly how molecular changes appear as data. Lowering the energy required for a jump slides the peak right, a bathochromic redshift. Requiring more energy slides it left, a hypsochromic blue shift. Hyperchromic and hypochromic shifts represent changes in absorption intensity. A spectrum is incredibly sensitive. Every single directional shift on this plot reveals a specific, measurable alteration in the underlying structure of the molecule. Finally, we have to consider the environment. In the lab, our target molecule isn't floating in an empty vacuum. It is surrounded by and interacting with a liquid solvent. If that solvent is polar, like water or ethanol, its molecules will dynamically interact with the target compound through forces like hydrogen bonding. When a polar solvent forms a hydrogen bond with the non-bonding electrons of a chromophore, it effectively anchors them down. This stabilizes the electrons, lowering their resting energy state, which artificially widens the vertical gap required to jump up to the excited orbital. Because that wider gap demands more energy to cross, the resulting absorption peak is pushed to a shorter wavelength, registering as a distinct hypsochromic blue shift on our spectrometer. UV-Vis spectroscopy links macroscopic physics with quantum mechanics. By measuring how light dims as it passes through a cuvette, we generate a highly precise topographical map of a molecule's structure, its concentration, and its dynamic chemical environment.